Today I'll be going over the OpenZeppelin implementation of ERC 721 Enumerable. Right now I'm using version 4.x, which is the latest version. However, the OpenZeppelin implementation is always changing and being improved upon. So the goal is really not for you to memorize how to use version 4.x, but rather for me to give you the tools so that you can analyze whatever source code or libraries you're planning to use in your project. So let's look at ERC 721 Enumerable by checking out the API reference. So here we see that ERC 721 Enumerable is an optional extension that allows enumerating tokens on-chain, often not included since it requires a large gas overhead. So this is an optional extension because it's not technically required as part of the ERC 721 standard, but it's very helpful for your smart contract to expose this. So this extension exposes three methods: total supply, token of owner by index, and token by index. Scrolling down, we can see the description. So total supply just returns the total amount of tokens stored by the contract. That's pretty simple. Token of owner by index returns a token ID owned by owner at a given index of its token list, used along with balance of to enumerate all of owner's tokens. Now this is pretty complicated, and when I first read this, I had no idea what it meant. It took me a couple of hours to understand it, and hopefully I'll be able to explain it to you to save you a lot of time. And then the last function here is token by index, which returns a token ID at a given index, blah, blah, blah. So that's also a little bit hard to decipher at first. So let's instead look at some examples. So let's say you've created a new smart contract for NFTs, similar to CryptoKitties, where each token represents a cat. And right now you have two users that own NFTs. So Alice owns the token IDs 4, 9, and 11, and Bob owns the token ID 13. In the ERC 721 standard, it's not required that the token IDs are created in a sequential ascending order. So the token IDs can actually be created in any random order, such as 4, 9, 11, and 13. Now let's say in your decentralized app you have a front end in which you want to expose all the cats that are owned by the user that's logged in. How would you do this using ERC 721? Unfortunately, if you're only using ERC 721 without using the enumerable extension, it's not possible. This is because ERC 721 only exposes two methods: balance of, which tells you how many tokens an owner owns, and owner of token ID, which tells you the owner of a specific token. With just these two methods, it's not possible to retrieve all of the tokens that are owned by an owner. You can only get the number of tokens they own, or you can find out whether a specific token is owned by a certain owner or not. Internally, in most implementations of ERC 721, including the OpenZeppelin implementation, the data structure that's used for ERC 721 is a private mapping, which will map from from the token ID to an owner address. And then the balances, which are used to keep track of how many tokens are owned by a specific address, is also another private mapping, which maps from the address to the number of tokens that are held by that address. So based on these two internal data structures, can you think of a way to expose a method that would be able to return all of the token IDs that are owned by an address? Feel free to pause the video and think about the different options. Unfortunately, with just those two mappings, it's not possible to have an efficient way to return all the token IDs that are owned by an address. One way might be to iterate over every token ID to address pair in the mapping, and then check if that address belongs to the target address. And if so, then you might store the token IDs in a list and then return that list of token IDs. However, that would be extremely slow because you have to iterate over the entire mapping. This is where the ERC 721 enumerable extension comes into play. It exposes these three methods here: total supply, token of owner by index, and token by index, to allow you to query all of the token IDs that are owned by an address. From the documentation that we saw earlier, token of owner by index is key. So here, it returns a token ID owned by owner at a given index of its token list, and you're going to use that along with balance of to enumerate all of the owner's tokens. In order to get this to work, the enumerable extension adds some data structures to our contract. Instead of just the two mappings that we had earlier, now we also have another nested mapping called own tokens, which is going to map from an owner to a list of own token IDs. We have another mapping called own tokens index, which maps from a token ID to an index of the owner tokens list. There are a couple others, but instead of just reading off this slide, I think it'll be easier if I walk through an example. As I'm walking through this example, Feel free to skip back to the previous slide to look at the description of these variables, or you can open up a window with the OpenZeppelin documentation so you can also see the descriptions. So let's say we're starting with a brand new ERC 721 smart contract and no tokens have been minted yet. And now we're going to mint the first token ID to Alice, and this is going to be token ID 7. So in this all tokens array, it's going to have a list of all of the token IDs so far that exist in this smart contract. So because the first token ID that's being minted is number 7, we're going to add 7 into this list. Now we're also going to update the all tokens index mapping. All tokens index is going to store the index of each token ID, and this index is going to be the index in the all tokens list. So for that first token ID, which is 7, we're basically asking what is the index of token ID 7 in the all tokens array. So looking in the all tokens array, we can see that token ID 7 is at index 0, and therefore we're going to store 7 with 0 in this mapping. Now for the third variable, owned tokens index, this is going to say for each token ID, what is the index of this token ID in the list of token IDs that are owned by a user. Let's use the example of token ID 7. Token ID 7 is owned by Alice, and Alice currently has just one token ID. So if we imagine a list of all the token IDs that are owned by Alice, it's just going to be token ID 7. And because there's only one of them, then this token ID is going to be at index 0. So that's where we're storing 7 and a 0 in there. And finally, for own tokens, this is going to store for each user the index of the token and also the token ID that's at that index. So this is very similar to own tokens index. It's kind of the reverse or like the corollary of that. So if we imagine all the tokens owned by Alice, there's simply just one token in there. And we want to say for that 0th index in that list of tokens owned by Alice, what is the token ID at the 0th index? And that one would be 7. Now let's walk through another example that builds on top of that to make it more clear. So let's say after minting token ID 7, we are also going to mint token ID 9 to Alice. So now we've added another token ID 9 to the all tokens list. So this means all the tokens IDs that exist in our contract are currently 7 and 9. Now when we update the all tokens index, we are now saying that for token ID 9, its index is 1. That's because in the all tokens list, the index of 1 points to token ID 9. So just to go over it again, in the all tokens index, we have token ID 7 pointing to index 0, because in the all tokens array at index 0, we have token ID 7. In the all tokens index, we have token ID 9 pointing to index 1, because at index 1 in the all tokens list, index 1 is pointing to token ID 9. And now we're also going to update the own tokens index. So this is asking for token ID 9, in the list of all tokens owned by Alice, what is the index of token number 9? So because token 9 is the second token ID that's owned by Alice, it's going to be at index 1, because the indexes increment from 0, 1, 2, 3, 4, 5, etc. And finally, own tokens is again going to be the reverse of that. So in Alice's mapping here, we're going to say that for index 1, it's going to point to number 9, because Alice has 2 token IDs currently. So the indexes will be 0 and 1, and they're going to point to 7 and 9. Now that we have these additional data structures, we can find all the cats that belong to a user. In this case, we can find all the cats that belong to Alice. So if you remember from the documentation, the first step in using the enumerable extension is to call balance of to get the total number of coins or NFTs that are owned by Alice. So in this case, she owns 2 tokens. Now in our own tokens, if you remember from the previous slide, we have Alice stored in the mapping, and it's pointing to 0, 7 and also to 1, 9. So 0, 7 means that for the index of 0, it's pointing to token ID 7. And this means that for the index of 1, it's pointing to token ID 9. So from earlier, because we know that the balance of Alice is 2, we can iterate over the indices from the range 0 to 2. And then we can just look up in the mapping Alice for 0, which will point to token ID 7. And we can also look up Alice 1, which will point to token ID 9. So just like that, after getting the balance of Alice, we can iterate over the balance and find that she owns token IDs 7 and 9. To generalize that a bit more in code, basically we're going to use the balance of to get the total balance of a user, and then we're going to call token of owner by index to enumerate all of those tokens. And basically you call balance of on an address and you get the token count. And then you're going to iterate over that token count, and then for each index, you're basically going to call token of owners by index. So here, token of owner by index, it accepts as arguments the address of the owner and also the index of that token. Not the token ID itself, but the index of that token in the list of tokens that are owned by that address. And then it's going to return the token ID. So this will return the token ID owned by that owner and a given index of its token list. So token list here is basically saying, let's imagine you had all the token IDs owned by that owner and you put it in a list. So the list will contain some token IDs, and then the indices in that list will start at 0 and then go 1, 2, 3, 4, 5, 6. So the indices will be consecutive numbers increasing. But the token IDs that are stored at each of those indices may not have any order to them. And then you can do whatever you want with the token ID after retrieving it. You might do something like look up the token URI and then display the image that's associated with that NFT or whatever you want. Just to reinforce this concept, I have a more visual explanation of this. So again, we're using the balance of address to get the number of tokens owned. And then for each index, we're going to look up the token ID from that private mapping. So to visualize it here, we have the indexes 0 and 1, which represent the token IDs 7 and 9. So this table here represents all of the tokens that are owned by Alice, which are 7 and 9. And again, token ID 7 is at index 0, and token ID 9 is at the index of 1. That's why when you look up the mapping, Alice and 0, you get 7. And if you look up Alice and 1, then you get 9. Now let's look at another example of how transfers work using the enumerable extension. Just a heads up, this one will be a little more complicated, so you can feel free to stop here if you think you've learned enough about enumerable extension. So first, let's look at the code itself in the OpenZeppelin GitHub page. So here I'm on the master branch, which is version 4.x, and we're in the ERC 721 folder. So we're going to look at the enumerable extension, which is in the extensions folder. So here we have ERC 721 enumerable. So if you want to dive into any of the OpenZeppelin implementation code, this is where you would look. So here again, we see the methods and data structures that we discussed previously, such as own tokens index, all tokens, and all tokens index. Then we have the token of owner by index, which is internally looking into that own tokens nested mapping. So here in the OpenZeppelin code, we have a method called before token transfer, which is called before a token transfer. And we have a couple methods like add token to all tokens enumeration, remove token from owner enumeration. Now all these additional crazy methods are needed because now that we're having these additional private mappings to keep track of the state of our contract, we also need to keep these data structures updated. And this is why the extension is so gas heavy. And that's why it's optional, because to do all this crazy handling, to be able to enumerate all of the tokens that are owned by an owner, you have to keep these mappings up to date at all times. So in particular, we're going to look at this method here called remove token from owner enumeration. So it's saying we need to prevent a gap in the tokens array. This is a little bit more complicated, so let's walk through an example first. So let's walk through this example of Alice transferring token ID 7 to Bob. The OpenZeppelin implementation is going to call before token transfer using token ID of 7, and then it's going to call that remove token from owner enumeration method that we just looked at. And here I've drawn the state of the data structures after the transfer is complete. So in this case, we're just transferring a token from Alice to Bob. So all the tokens that are in the smart contract have not been changed. We still have token 7 and token 9. We did not mint any new tokens. We did not burn any existing tokens. So that array is unchanged. The all tokens index is also going to be unchanged because the all tokens array was unchanged. So basically in the all tokens array, this is saying that that index 0 still points to token ID 7, and index of 1 is still pointing to token ID 9. However, these last two mappings have changed. So the own tokens index is going to represent the index of the token as it's owned by that user. And this is going to be the only token that Bob has. So therefore, its index is going to be 0. And now Alice owns token ID 9, and this is the only token that Alice owns. So in the array, if you imagine the array of tokens that are owned by Alice, the token at index 0 in that array is going to be for token ID 9. And then again, own tokens is kind of the opposite of the own tokens index. So this is saying that for Alice, the index of 0 is pointing to token number 9, and for Bob, the index of 0 is also pointing to token ID 7. Now, what was all that crazy business in the comments about saying that no gap is allowed? If you remember from back here, it says to prevent a gap in the tokens array, we have to store the last token in the index and then blah, 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 do some other stuff. So to visualize this, it's easier to start with a new example which has more tokens in it. So let's imagine that you have a new contract and you have some owner that owns 5 tokens. They own token IDs 5, 17, 23, 1, and 7. So in that list of all the token IDs that are owned by that user, we have those 5 tokens in there, and the indices go from 0, 1, 2, 3, and 4. And let's say now the owner wants to sell and transfer token ID 23. The thing is, we have to now remove token ID 23 from this list. However, if we just take 23 out of there, there's going to be a gap. Now, why is this gap bad for us? The gap is bad because it would break the logic that's underlined here in red. The point of using ERC 721 enumerable is that you can use balance of to enumerate all of the owner's tokens. In this logic here, we're calling balance of, and then we're going to iterate over all of the indices from 0 to that token count, which means that if there's a hole in that token count, then we are not going to be able to access the token ID there. So in order to keep this for loop working, we have to make sure that all the indices from 0 to token count are indeed pointing to actual token IDs, and we can't have a gap in there. You can imagine here that if we just took out this token 23, you call balance of on that user, now it's going to return 4. But now if you want to iterate over the indices from 0, 1, 2, and 3, there's going to be this weird gap in here. So in the code, we instead have to swap and then perform the deletion. So we want to sell token 23. So then we're going to swap token ID 23 with token 7. And then finally, when we sell 23, we can cross out 23. And then that way we can still use the balance of to iterate over the tokens by iterating from 0, 1, 2, and 3, and this is still pointing to valid token IDs. To put this another way, by switching the token that you're transferring to the last index, this will preserve the ability to use balance of to find all the tokens that belong to the address. So here, we swap token ID 23 to the last one, and then we're crossing it out because we're selling it to another person. And that way, when we call balance of, now we get that there are 4 tokens in the balance, and then we can iterate from 0 to 4, so we're going 0, 1, 2, 3, and this way we can still access valid token IDs. Now you might be asking yourself, who cares? You don't really need your own NFT smart contract to inherit from and use the enumerable extension, which is also really gas heavy, because maybe you can just rely on Moralis and Alchemy because they have APIs where you can just pass in an address and you can find all the NFTs that belong to that address. Now, the way that Moralis and Alchemy do this is that they have some listeners that are listening to all the block transactions on the blockchain, and then they're looking for transfer events that are emitted whenever you transfer tokens on ERC 721 or 1155, and then they index it into their centralized database. The problem with this is that this is very centralized, and now you're relying entirely on Moralis and Alchemy. So if Moralis or Alchemy have a bug, or maybe they suddenly decide to start charging you per request way more than you can afford, then you have no way of enumerating all the tokens that are owned by an owner. Whereas if your smart contract does expose the enumerable extension, then you can enumerate the tokens without relying on the centralized third party. And now for my last point, which is that nothing is free. If you're going to use something from OpenZeppelin or some other library in your smart contract, it can really pay off if you're able to dig deeper into the source code of that library to understand what it's doing. If there's a lot of new awesome functionality being exposed by this library, there has to be a cost to it. For example, Maybe more data structures need to be maintained, which will equate to higher gas fees. If you're deciding about whether to use that library or not, you have to make careful decisions about the trade-offs and whether and what kinds of functionality is really needed and exposed by your smart contract. If you anticipate that your smart contract is going to allow very few transfers of tokens between users, then the enumerable extension is a pretty good option because it's the writes that are really expensive. Updating all of those private mappings is expensive. But if you're not doing any transfers, and instead you're mostly just doing lots of reads, then using that extension is a pretty good idea. On a similar note, maybe you've taken a look at the OpenZeppelin library and you decide that it's not quite appropriate for your use case, and you might need to modify their code a little bit to suit your use case better. Then you really have to understand your use case, like whether you need slow writes and fast reads, or whether maybe you need fast writes and slow reads. The concepts from Web 2 still apply to Web 3. You still have to have a solid understanding of how people are going to be using your smart contract, and then write that code accordingly. If you made it this far, definitely give yourself a huge pat on the back. I know that the enumerable extension is pretty complicated and pretty hard to explain. So if anything is unclear, please leave me a note in the comments and I'm happy to explain it more. Please give a like and subscribe, and I hope to see you in the next video.